Hi, have you ever wondered on the magic behind the automatic systems of credit cards, the ISBN in books, and the barcodes in various products, or the universal product code, and the magic behind cryptology? Well, we will be teaching you today the various applications of modular arithmetic. Remember that in modular arithmetic, we are paying attention to the remainder when the dividend is divided by the divisor. For example, 14 modulo 10. We divide 14 by 10, we get 1.4. The 4 here is the remainder, so it is the answer of 14 modulo 10. Now, we will dive into the first application of modular arithmetic, the International Standard Book Number, or the ISBN. So every book that is cataloged in the Library of Congress must have an ISBN. So for example, in this book, it has an ISBN of 978-0130273956. So this 13-digit numbers was created to help ensure that orders for books are filled accurately and that books are cataloged correctly. So the first 3 digits of an ISBN are 978 or 979, followed by 9 digits that are divided into 3 groups of various lengths. This indicates the country or region, the publisher, and the title of the book. The last digit or the 13th digit here is called the check digit. We label the first digit of an ISBN as D sub 1 and the second digit of this ISBN as D sub 2 up to the 13th digit as D sub 13. The check digit of this ISBN is given by the following modular formula. So we have to remember that the 10 minus here, the 3, and the modulo 10 are constants. So if D13 is equal to 10, this is equivalent to 0. So your check digit is 0 if, again, your D13 is 10. So it is this check digit that is used to ensure accuracy. For example, the ISBN of the book Mathematics in the Modern World, Philippine edition, published on 2018, it has an ISBN of 978-971-239357. So we'll write this on the board. The ISBN of this book is now given here. Suppose that a bookstore clerk sends an order for that book and inadvertently enters the numbers, and the store clerk inadvertently transposes these numbers 3, 9. So if we are the receiving clerk, we will be calculating the check digit in this following process. So we have now substituted the values given in this ISBN to the formula given previously. So we have to calculate this part first. So D13 is equal to 10 minus, and this part is equal to 142. Then we put modulo 10. Then after this process, we will then calculate this first. So 142 modulo 10 is equal to 2. Then 10 minus 2 is equal to 8. Since we arrive at 8 instead of 0, we know that the given ISBN is invalid. Moving on to the next example, suppose we are to find the 13th digit or the check digit of an ISBN. We are to perform the same formula and process. So for example, using the same ISBN from the first example, the correct ISBN, this one, suppose we are only given 12 digits and we are to calculate the 13th one, or what we call as the check digit. We calculate that through this process. So we now substitute these values to the formula in calculating the check digit of an ISBN. we calculate again this first part. This one is equal to 130. Then we copy modulo 10. We calculate this 0. So D13 is equal to 10. So since we get 10, remember that if we get 10, this is equivalent to 0. Therefore, the check digit of the ISBN of the book Mathematics in the Modern World Philippine Edition is 0. To conclude, to look for a check digit, you calculate first the given 12 digits of the ISBN using the given formula and make sure to not transpose any number. Also, getting the validity of the ISBN, the number you will arrive must be the same with the check digit or the 13th digit of the ISBN given.
So now we are going to talk about UPCs and how can we use modular arithmetic in checking if UPCs are valid or not. So what are UPCs? UPCs are a coding scheme that is closely related to ISBN. The uses of UPCs, or more commonly known as barcodes, can be seen in grocery stores, department stores, or any store that we go to. UPCs are technically used for tracking or keeping inventory of the items and for faster checkout just by scanning the UPCs or the barcodes in grocery stores or large-scale businesses. So now we are going to use modular arithmetic in checking a particular UPC if it is valid or not. So here we have an example of a UPC. UPCs are technically 12 or 13 digits, but here we are using a 12-digit UPC, which is this. So now we're going to use modular arithmetic in checking whether a UPC is valid or not. Now a UPC may be a 12-digit or a 13-digit code, but here we are using a 12-digit code, which is 0421-000-5264. And now we're going to use X subunits to assign to these numbers to use for a better or faster solution. As you can see here, our first digit is assigned to X sub 1, and this goes so on and so forth up to the last digit, which is 4, which is assigned is as X sub 12 equals 4. So now we are going to move on to the solution to check whether this is valid or not. So as you can see here, we have copied our UPC code, and we have also our solution or the formula for checking whether a UPC is valid or not. So we can see here that we have used the X subunits up to the 12th digit, but here we have pattern. For every first and skipping one X subunit, we add 3 to the formula. So it can be 3x sub 1 plus x sub 2 plus 3x sub 3 plus x sub 4, and so on and so forth up to the last digit. And this solution should be congruent to modulo 10. So in the next step, as you can see, we have already substituted our X subunits to the formula. So it will now be 3 times 0 plus 4 plus 3 times 2 plus 1 plus 3 times 0 plus 0 plus 3 times 0 plus 0 plus 3 times 5 plus 6 plus 3 times 4 should be congruent to modulo 10. So now it will be 0 plus 4 plus 6 plus 1 plus 0 plus 0 plus 0 plus 0 plus 15 plus 6 plus 12, which will be equal to 44. So for the last steps of this process, we already have the sum of all our numbers that we use in our formula. So how can we know that 44 is congruent to modulo 10? This is simple. We simply subtract 0 from our sum of our numbers. So the difference of this number, which is 44 minus 0, should always be divisible by 10. So 44 minus 0 is still 44. 44 divided by 10 is 4.4. Therefore, since you have determined that 44 is not divisible by 10, this UPC is invalid.
Did you know that the number sequence in every credit card, debit card, or ATM card is actually not just a random string of numbers? It's a generated code created to keep your card and your information safe. This is done through a modular arithmetic called the Loon formula. Let's take this credit card number for example. To find out if this credit card number is valid and won't get declined at the counter, let's apply the Loon formula. To use the Loon formula, we need to double every other digit in this sequence and then sum all of those digits and find the resulting number. If the resulting number is divisible by 10 or congruent to 0 modulo 10, then it is potentially a valid card number. To know what numbers we need to double, let's identify our check digit first. This is the very last digit of the sequence. The digits we have to double alternate, going from right to left, starting with the number that comes right before the checked digit. So our sequence is going to look like this. With the underline representing the numbers, we have to double. Let's go ahead and double those digits. Before we continue, if the double digit results in a number greater than 9, then you must add those digits again into a single digit number, like with the case with these ones. Now all you have to do is take the sum of each digit in the sequence. If the resulting number is divisible by 10 or congruent to 0 modulo 10, then it is a valid card number. Since for this example we got 70, which is divisible by 10, this card is valid.
Now let us talk about cryptology. Codes on books and grocery items are secret codes that are used to send messages between people, companies, and nations. It is hoped that by devising a code that is difficult to break, the sender can prevent the communication from being read if it is intercepted by an unauthorized person. Cryptology is the study of making and breaking secret codes.
Suppose we have here the word James the Great. With a key of 5, the encrypting congruence is C plus P plus 5 mod 26, replacing P with the numerical equivalent of each plain letter of the plain text. Performing a Caesar cipher by moving each letter 5 positions to the right in the alphabet, we would shift each letter by 5 positions. A Caesar cipher is a basic substitution cipher where each letter in the plain text is shifted a certain number of places down or up in the alphabet. Our P here is 10, as J is the 10th letter of the alphabet. M here is the key where the number of the times we shift to the right. C represents the cipher text, P represents the plain text, and M represents a constant shift or our shift value. Mod 26 indicates the use of modular arithmetic with the modules of 26.
Now you have learned the different applications of modular arithmetic. Remember that the essence of mathematics is not to make simple things complicated, but to make complicated things simple.